Okay, we're back. Quick follow-up. One more way to understand the chain rule. We talked back in class about the Leibniz notation for differentiation, and a certain level of comfort with the Leibniz notation I think is needed and is also really helpful. And one sort of a really simple way of understanding why the chain rule is sort of obviously true is to consider a real world example. So imagine that you have a cylinder, and imagine that for some reason we happen to know, so I'll just write we know, that at time 5, oh, and this cylinder is like filling up with water or whatever. No, I take it back. The cylinder is not filling with water. The cylinder itself is growing according to some process. And okay, suppose we know that at time 5, dr dt, which is how people pronounce it, is growing at a rate of 2 centimeters of radius per 1 second of time. In other words, more simply, just suppose that we know that the radius of this cylinder is growing, and specifically the rate at which this radius is growing is 2 centimeters per second. So at every single second, the radius is growing. It's growing at a rate of 2 centimeters. So in a span of a second, it will get 2 centimeters bigger if it continued growing at that rate. And I don't know if this cylinder is growing at a constant rate or not, but I'll just tell you that at this particular moment, at time 5, this is the rate at which the cylinder is growing. Okay, I think that's pretty clear, and that's what dr dt means, right? It's the rate of change of the radius with respect to time. So for a tiny second of time, the change in the radius that we would expect is 2. Okay, suppose I also know at that same time, t equals 5, I happen to know that dv dr is 3 cubic centimeters of volume per 1 centimeter of radius. Now, I think if I told you the height of this cylinder, this is something you could calculate. But never mind that. I'm just telling you now that, that at this moment, the volume is changing in a certain way. And, well, what is the change in volume? The answer is that we get another 3 cubic centimeters of volume for every change in the radius. So that's what dv dr means, right? For a small change in the radius of the cylinder, how much volume of the cylinder do we expect? And the answer is, if the radius changes by 1 centimeter, if the radius gets 1 centimeter bigger, then the volume of the cylinder increases by 3 cubic centimeters. And that's specifically at time 5. Okay, and now finally, what if what I wanted, suppose, is to know dv dt at t equals 5. In other words, when I even write dv dt, what I mean is, what is the rate of change of the volume with respect to time, or more simply, how fast is the volume changing? In a tiny, tiny bit of time, how much new volume do I get? Well, in this case, I feel like the answer is just obvious. If what I want to know is the rate at which the volume is changing with respect to time, then of course I can just say, well, how fast is the radius changing with respect to time? And how fast is the volume changing with respect to the radius? And here it's clear that multiplication is appropriate because rates just multiply. So, if I want to know the rate at which the volume is changing, and I am told that the radius is, so I sort of just want to multiply here basically, right? What this is really saying is that at time, and so I can just do this, right? What is dr dt? It's 2 centimeters per, I'll just say 2 centimeters per 1 second. Maybe I should write of radius, times, and here I expect 3 cubic centimeters of volume with respect to every 1 centimeter of radius. In other words, if I want to know the rate at which the volume is increasing, I just say, okay, well, for every second that goes by, I'm getting an extra 2 centimeters of radius, and for every centimeter of radius, I get an extra 3 cubic centimeters of volume. And so the answer is, of course, that I will get 6 cubic centimeters of volume per every 1 second. And the conclusion is that you just multiply these, obviously. That dv dt is dr dt times dv dr. Okay, and that sort of maybe, this is the follow-up to what I just did in the other video. I think this sort of explains in some intuitive level that, oh, of course you multiply these. Because that's how rates work. Rates multiply. That's kind of what the chain rule says. Okay, good. This was something that I think I did in period 3, but not in period 4 or period 6. So good. All right, bye.